All right, folks, welcome. I guess we should just give it another few seconds for some people to join in because we have a good few signups, and then we can kick it off.
We have currently 26 attendees and counting. Good job.
So I think maybe probably better off to give another minute or so just to build a safe side. And I'll catch up. I'll make it sure. All right, folks. Welcome to this webinar. Super excited to have our presenters today. I'm going to go quickly over some introductory slides, and then we will actually switch over to the best part of this webinar, of course. So this is a part of a pre-series SuriCon webinar series, actually. What we aim to do is actually spread the word around because our guests today, Joe Stroschein and Francisco Perdomo, will actually be giving out training, hands-on training at SuriCon as well. So looking forward to that. But I'll let them speak in much bigger and more detail and much more knowledgeable detail than me about that in a few seconds, literally. So we have a few just a couple of information notes. The Open Information Security Foundation, what is it? It's actually a US-based non-profit organization that is actually organizing a community and support to open source security technologies like, for example, Suricata. And Suricata is a project that sits under OISF. So funding for Suricata comes from world-class security organizations, some of the biggest and the top in the world, and plenty of them. And that are using and utilizing Suricata and that are committed to our mission. So thank you very much to all the consortium members for that support. They're essential to our mission and our daily operations. What is Suricata? For those of you that are familiar about it, Suricata has grown a long way. From 2007 up until now. It's constantly evolving thanks to consortium members, thanks to huge community, thanks to donations, including of code and funding from a bunch of different organizations. We cannot be any more thankful than that. It has evolved to be a formidable, actually, network security monitoring system that produces an array of data that is actually can improve your network visibility, security posture, and all that via way of providing very detailed information about all sorts of protocol transactions, flows, extracted PCAPs, extracted files, PCAPs, alerts, and similar other metadata coupled to it. So an essential tool of the network security monitoring project, essential tool of the security stack of any organization, I would say. Now, please go over to our website for more details. If you'd like to, we'll be happy to help out as well. However, without further ado, as I mentioned, very thankful and a great pleasure and actually honor to have a couple of people or colleagues from the security industry that will actually show us something quite different for these types of webinar series. And we have the possibility and opportunity to have them doing a 2-day full hands-on training at SuriCon Madrid, which is our 10th SuriCon. So very thankful. Gentlemen, I'll transfer it over to you, Josh, Francisco. Thank you very much for being here. Stage is yours, folks. And I'm going to stop sharing now.
Okay. My turn to start sharing. Please tell me when you see the presentation.
I see your screen, sir.
Perfect. Okay, well, hello everybody. My name is Francisco. Everybody calls me Pancho. Yeah, I'm a security engineer that works in Virus Total. So basically, I do some research, I do some threat intel. I work a lot with YARA rules. That's what we are going to talk about today. Let me present yourself. Josh, if you want to present yourself.
Yeah, here. Hopefully you can hear me okay. My name's Josh. I am reverse engineer with the Flare team at Google. I guess formerly Mandiant. Mandiant was acquired a couple of years ago now. Often do speaking and training based in South Dakota. I was previously a professor at Dakota State University. Did that about 10 years. Retired from the Air National Guard, doing a number of different careers there. Used to work with OISF for several years, actually, and Peter and Juliana. So it's great to be kind of back in the fold here. In fact, I wore my SuriCon, I think this is 2018 in Vancouver shirt. So this is the oldest one I have. Although my first SuriCon was in Prague, I wasn't there long enough apparently to get a shirt though. So looking forward to chatting with you all. I'm going to be spending a little bit of time in IDA and doing, looking at YARA rules at a little bit more of a lower level.
Perfect. So today we are going to give you a little introduction on what we are going to teach about in the SuriCon this year. So basically, we're grabbing a little section on specifically YARA rules, and we're going to show you. I'm going to give a short introduction, and then Josh is going to continue with this. So hope to see you in November in Madrid, and let's start. So the idea here is to show a little bit of what is YARA, what's the capabilities, and how much can we do with it. So for the guys that have never seen YARA, this is like the minimal YARA that you can get. Basically, you have YARA is a tool for pattern matching. Yeah, you can search for files with specific patterns. In this case, this is like the very basic stuff of a YARA rule. It's also like this syntax is you have the title of a rule, the strings that can be contained inside, and the condition of this rule is if it matches these strings in a file, you will get a match. So let's go straight for the hands-on. So this is another minimal YARA that I created here, and we have a folder here with lots of malware files, including Windows binary files. Yeah. So anything that can be matched here, it will appear. So let's start by grabbing our terminal and running a simple YARA. This one is called minimal YARA. If I use the /r and I try to search in the directory I'm sitting at, in this case, I will only find my base YARA. So a simple way to match a file is search for the strings that a file has. So it's really easy. Let's do strings on a random file. Let's say malware 05. So I find here an interesting string that I want to match. Maybe this string is very particular, and it is interesting for me to search it in a YARA rule. So I can copy it and add it in a YARA rule. This way, if I run again the same minimal rule, I will match with my YARA and the next file. But maybe I don't want to use the full string. I just want to search for files that only match with ping text. So probably if I'm searching in a bunch of files that might be malicious, I can find a lot of files that can do a ping. So I tested it again, and then I find that I have, I don't know, more than 10 examples of files that match this rule. But also I'm matching Windows binary tools. So YARA rules have to be tuned with several conditions I have to create false positives and exclude them from my conditions. So this is like the very basics that you have to understand to start creating YARA rules. So returning here, basically when a rule doesn't catch anything besides the initial sample or the basic YARA rule, it needs improvement. So this is something we just did. It's like we started messing with the strings that we were matching. Yeah, so we started catching more files. But then it started catching too much stuff. Maybe we started getting false positive with the Windows binaries, for example. And we know we don't want to catch the Windows binaries because we know that those ones, in particular because we chose them, they are goodware. So we have to exclude them. So if your new roles catch new stuff, if you're putting this in a security tool and start catching new stuff, that's great. If it stops catching things, it's not that good. And if it starts having false positive again, that sucks. So YARA rules need to be constantly monitored and updated. So some ways of reducing noise, it's, for example, get some context on what you're catching and maybe create some filters or create some special conditions to catch less stuff or be more focused on what you're trying to catch. String counts, sometimes whitelisting the known goods, for example, the Windows binaries, yeah, using negative conditions, and there are lots of ways you can reduce noise. So this is one of the demos that we have in the workshop, at least a part of it. And what we have here is a basic ransomware YARA rule. So we grabbed a lot of the messages that are in the ransom notes and grab like the most repeated text that we found in these files and say, okay, most of the ransomware or all of the ransomware is going to have some ransom node. So if we put them all together into a YARA rule, we will catch a lot of ransomware. It's not that bad of an idea, but very quickly we are going to discover that this rule in particular, it's really wide, so it catches a lot of stuff. So let's do more or less the same. YARA generic ransom YARA, and let's search in the same place. So now we see that we are catching a lot of stuff, yeah, from the malware files, but also from Windows binaries. Yeah, some of them, for example, are catching this encrypt text. That this encrypt text could be anywhere. It's really generic and it doesn't help us. So one way of tuning this YARA rule is just commenting this line and say, okay, let's grab like such only these slices of text. Run it again. And here we see that we catch much less files and probably some files that we didn't want to filter out. But it's interesting to check on, okay, what did we catch? So if we run strings on mal10, for example, and we grep on encrypted, encrypted, it's the easy one. We can see part of the text on the ransom node. Let's do something more interesting there. So basically here we are reading specifically the ransom node. So we could search for other files that that contain ransom nodes, checking what are the ransoms, and we could start splitting the YARA rule to catch specific ransom nodes. But here the thing is, with this generic ransom YARA rule, we don't know what we are catching. We know that we are catching like really clear text that this is a ransom note, but we are not actually catching the ransomware. Maybe a lot of this is false positives. Maybe there is a lot of noise inside here. Maybe one of these mal files, it's just like a Windows binary renamed. So we need to have better ways of actually detecting a specific file and making sure that this file is related to a malware family in particular, that it does what it pretends to do. So basically, this is the life of tuning files, catching generic rules, and trying to accommodate them, like understanding what the malware is trying to do. For now, we didn't even open a malware file, but we started grabbing some files and having an idea on what we can catch with YARA. But if we count all the files that we catch here, there are more or less 14 ransomware files, but I know for a fact that in our sample set, we have like 20. So there are a lot of files that their ransomware nodes are not in clear text or in very basic, and they are not in clear text for sure. So we are not catching a lot of files. So I'll give the word to Josh now, and he will start to show you how to investigate more a file and not just the random strings that can happen inside of them. So up for you, Josh.
Okay. Let's see. I'm going to switch here and share a screen. Give me just a second. All right. Hopefully everyone can see
your screen, sir. Yep.
All right. Awesome. Can open up the chat and everything too, because then it feels a little too alone without seeing your faces in the chat here. Okay. If anyone has questions along the way here, please feel free to queue them up in the chat. I don't know, Julian, is there like an actual Q&A part to the webinar?
Is.
Yeah. Okay.
Yes, there is. And I'm checking that constantly.
Okay. Happy to answer those as we go, or we'll have a little bit of time at the end. I do have to warn everybody because after 10 years of being in academia, I've learned to talk just nonstop. So hopefully I'll make sense of this. The goal here, I had some slides, but I think in the interest of time, I'm just going to jump right into the demo. What we're looking at is everyone's likely familiar with Lockbit. If you're not, you could do a search in your favorite search engine. You'll find plenty of information about them. Very notorious ransomware as a service group that were subject to law enforcement action here earlier this year. I don't know, along the way, though, somebody decided, one of their affiliates or somebody that was within that organization or that group leaked their builder. And the idea behind this builder, as you're seeing here, this is the code. Their affiliates then, because they operated in this sort of affiliate structure, the affiliates could take the builder, they could use it to generate the actual ransomware that they would then essentially deploy into our environments and ransom systems. The builder is fairly straightforward, from a user perspective.
Sorry, Josh.
Yeah.
In the screen, we don't see the code, at least I don't. We just see the list of files.
Yeah, that's okay.
Okay.
Do you see my arrow right now?
Yeah, okay. But
Okay.
only a list of files. I don't know what you wanted to show.
Yeah,
That's why I interrupted. Sorry.
Let me see if that. Can I see my own screen? I don't know. Yeah, if you see the arrow and the list of files in the Explorer, then we're good.
Yes, sir. We're good.
Awesome.
Yep.
Okay, good.
Sorry,
So anyways, I can point you to the files here if you want. You can go find it. But the idea is that you use this builder, you run the dispatch script, and then it creates your ransomware. There are a couple of things I want to talk about here. We'll do a little bit of triage analysis. We'll get into the actual code here, do a little bit of work in IDA. Of course, this is all going to stem around our YARA rules, and decided to use community-sourced YARA rules because I think that's a common pattern. You encounter something or you're using rules that come from the community or you're contributing those yourself. The builder will produce a bunch of different samples. lb3.exe and lb3_pass.exe. Those are going to be the two primary executables. The _pass is basically a packed version. It's going to have all of its primary code obfuscated, encrypted, and it's going to require a password in order to decrypt that during runtime. So that's really an interesting but not a new technique for anti-analysis, because if you were to recover that binary and provide it to me as an RE and ask me to reverse it, as long as they implemented that password properly, I won't be able to get very far without it. It also works like in sandboxes. So you recover the sample in your environment, you put it into a sandbox, it doesn't run properly because you don't provide the password. So you would need to have the context. Something has to download and drop that, and part of that execution chain would then be the password. There are other samples. There's some DLLs and things that are going to have very similar type of capabilities, but we're not going to really worry about those. And then the passwords are going to be in these text files. So, but we don't need the passwords for this right now. What I wanted to focus on is just these first two binaries to talk a little bit about the difference here. Let's go with lb3_pass.exe. So this is going to be the protected. The tool I'm going to use is called Detected Easy. And if you're not familiar with the Flare VM, FLARE-VM, maybe you're familiar with Remnix. It's a similar tool or similar setup, or I guess like Kali as well, Kali Linux, and that it's just it's a project on GitHub. It's maintained by the Flare team, and it's designed to get you a Windows VM set up and configured full of RE and analysis tools. So that's everything here is just a stock Flare VM. If you go to the GitHub, you can find instructions on how to install it. The tool that we're going to look at here is called DEI, or Detected Easy. And this is oftentimes used as a triage tool for PE files, portable executables, executable files for Windows. There's a lot we could cover in this tool. Signatures down below are going to be oftentimes the first thing I look for to see if it can help me detect if this is protected or packed or some major technique of obfuscation. When it doesn't, there are other behaviors or characteristics. And one of those would be the entropy. There's a little entropy icon here and those rows of buttons. And what the entropy is going to do is it's going to measure the entropy on a scale of 0 to 8 across the file and then across the different segments of the file. And the closer you get to 8, the higher the entropy, the more likely it is compressed or encrypted content. So you can see with our packed file, if we hadn't known that, if this was the first time we were looking at these binaries, seeing entropy like this, where your entropy graph across this file is almost all the way pegged. I mean, we're in full burner at this point when it comes to the entropy. That would be a pretty good indication that you're dealing with a packed sample. Packed just meaning that a large chunk of the code is going to be obfuscated. Now we have this little dip here, and this little dip, we can actually use the tool here to explore the sections. The sections are just going to be different parts of the file, of the executable file that gets loaded into memory. There is this .itext section here. You can see right there. And that's this little thing here. And that would make sense then that could be the location where this whole, where there's code that's responsible for doing the deobfuscation, right? Because in order for this to execute properly, or anything that has obfuscation, there has to be code that isn't obfuscated that can run properly under the CPU to deobfuscate the later stages. Now let's close this, or at least let's switch to the other sample, lb3.exe. Similar in terms of the signatures, there's just some generic stuff here. There isn't anything that says, "Ooh, this was packed by Packer XYZ." Those are usually the most helpful. But if we look at the entropy, you'll see there's quite a difference here. And the primary difference you can see is this section, which is, I'll highlight that there, the .text section, that has very normal entropy. And I would say normal is a bit of a relative term, but generally anything under a 7 measurement, I would consider in that likely not obfuscated range. So this looks to be like it's not obfuscated, which could tell us then that maybe we're dealing with a sample that isn't packed. However, we still have, let's highlight the latter sections here, P data and data, these two sections, right? And again, this is just, look, you think of the file in a sequential sequence of bytes. This is just the content that comes towards the end of the file. This still has very high entropy. And so while this sample, the short answer is this is the unpacked version, and likely one that they wouldn't distribute, because the whole purpose of adding that anti-analysis and the packing and all those different layers is to slow down detection. Even with the unpacked version, there's still a region of this that is protected or encrypted. And that happens to be, in this case, things like the important strings and the ransomware note. So that's still protected, even though the overall binary isn't. That presents challenges when it comes to detecting these samples, because in a static state, depending on what sample we get, it's going to be still very difficult in order to come up with a YARA rule that's going to be able to detect this, because we don't have the strings, much like you saw Pancho exploring earlier, to kind of hinge our YARA rules on. That's where we talk about binary patterns or hex sequences, and we try to create rules that are based off of the actual underlying code. And that's what I wanted to just spend the last little bit of time here talking about. To do this, I thought it would be fun to check out some community rules. VirusTotal has the use of YARA rules and crowdsourced YARA rules. Abuse.ch is another great project. If you haven't checked that out, that would also be worth checking out. Abuse.ch has this YARA-ify project, and here you can find the YARA hub, and I just did a search for Lockbit, and this was one of the rules that came up. I didn't choose this rule for any other purpose than illustrative purposes. So I'm not saying it's a great rule, I'm not saying it's a bad rule. It was one that was shared for the community to use, and it's being used in this Abuse.ch ecosystem. Now, you can see the context of the rule. There's some metadata and some different information that YARA Hub requires in order to publish rules here. You can publish rules, it's all free. We have then our strings, and this is probably the area, well, this is the area I want to focus on. What do these strings tell us? Well, we have 3 variables, 3 patterns, code 1, code 2, code 3. So I guess it's suggesting through the name that it is a code pattern. We could also probably come to that conclusion just by looking at these sequence of bytes. But what do these bytes tell us? Right? It's really hard to understand the context of this, because likely these are patterns based off of code. And unless we have the ability to go look at the code, it's really hard for us then to take this rule, digest it, and really understand what it is and what it isn't telling us. That's different than the strings, because strings are just by nature more easy to read because they're strings. They're meant to be human readable. And again, strings are important. Our ransomware sample here, as with others, and pretty much every program that I've ever looked at, in order to do something useful, it has to have strings. It's just, where are those strings? How are they protected? When are they unprotected, decrypted or deobfuscated in order for use? There's some other information here, or some other checks that we'll get into, looking for PE files and file size, and sort of a flow here in the condition that you can also take to help narrow and sort of pre-filter your what your rule will match on, so that you can get a high true positive rate and hopefully a low false positive. But we won't have time to cover that here. As far as this rule, I'm going to blow up the font just a little bit larger here. On the Flare VM, YARA is already installed. You may have heard there is YARA X that is now in beta. So we talk a little bit about that in the training as well. But we're just using, I don't know if this is the most recent version, but it's really close. I set up this Flare VM a couple of months ago now, so I might be out of date. But we have YARA. I have my Lockbit 3 YARA rule. So you can see that just here in Visual Studio Code. No modifications to it, just copied it right out of the YARA Hub. And let's do a recursive option, and let's scan our leak folder and that build directory. Okay, so we can see we have 2 matches. We have a DLL and the underscore pass. What's missing then are the other versions of the ransomware that aren't password protected. Now, again, those probably aren't going to be the ones that get distributed, but you might still want to have coverage of them anyway. So this is interesting to know However, if you didn't understand the context in which these binaries were built, or maybe you didn't even have the samples as you were creating or testing these YARA rules, it can be hard to understand that. With YARA, you can also do -S. And what this will do is this will spit out where the matches were. So we'll take a look at, let's do this one here. So the password protected. And this is telling us that through the detection engine, code 2 and code 3 were in fact the two variables that matched. So that means that this sequence of bytes shows up somewhere inside that binary, but not in the unprotected version. So I'm kind of curious as to why that is. Now, if we wanted to figure out what these bytes actually represent, right, we have to go digging into these binaries to figure that out. And we'll try to answer all of these questions here in the next few minutes. Let's see. So let's go back to our folder, and we've got our two binaries that we've been exploring. This is the one that it matches on. So let's open this up with IDA. Now, if you're not familiar with IDA, IDA is a disassembler with the decompiler. This is the free version. There is a limited free version. Ghidra is open source. It's a similar tool. It's from the NSA. You can use either one here. They're going to give you pretty similar results. And the goal, though, is that we are now actually using these tools to analyze the code. And in particular, we want to try to figure out what those bytes represent. Now, before you do that, I'm condensing a lot, right? I'm relying on my experience to read disassembly, that is assembly. I'm not going to use the decompiler for this particular demo, but that's usually something that I also use when doing any sort of reversing. And there's just a lot, right? And so if you don't spend any time or a lot of time in IDA, there is absolutely a learning curve here. And hopefully, a big part of this motivation was just to show, you see a lot of rules out there that are written based off of strings. And then, of course, far fewer that are based off of code patterns. And this is likely one of the reasons why. It's just more difficult. So what IDA will do is it'll take us to the entry point, the address of entry. And this is where execution of the program typically begins once it's been loaded into memory. This is the protected version, right? And I said that this code that would seem to kick off this whole deobfuscation process is going to start in the iText section. IDA is set up here by default to show you the segment or the section name, as well as the virtual address, and then the different disassembled instructions. So this lines up. We're in the iText section. This is our entry point, and we've got some function calls. Now, again, if you're not real familiar with assembly, don't worry. A call instruction is just that. It's calling a function. So there is a function that exists at location 419000. And IDA, even though we're not running this in memory right now, IDA is acting like an operating system loader. And it's showing you more or less what this program will look like when it is run in memory, or if we decided to debug it. Now, if we navigate into this function, you'll see that there's a fair bit of logic here. There's going to be a number of other function calls. Sometimes what I'll do just to get a sense of what I'm looking at is you can do cross-reference graphs. And what this graph will generate is all of the function calls from where we're currently located, right? And this doesn't look terrible, but I mean, each one of these functions could have a few lines to thousands of lines. So we don't really know until we start digging into it. There are no API calls, right? So I don't see any Windows API calls in here. There's not a call to virtual protect or virtual alloc or write process memory. So it's kind of hard to say, but it looks like this is probably all custom logic that was created by the authors. Now, it also stands to reason that if this thing is in fact packed, which we suspect, and this is legible, readable code, that this likely has something to do with the unpacking logic that more or less will come first before the rest of the binary can execute properly, right? So we've got some good suspicions here that this is our function that's responsible for that. Now, if we continue and just, again, kind of glance around at these next calls, notice with this next function call, and we're in this graph view. So I'm going to go to options and turn on line prefixes. We're in the text section. And we know that the text section had a high measure of entropy. So likely this is still obfuscated, and that would be the case. IDA will still try to disassemble. So it looked at the bytes that are there. It tried to disassemble it. The results were these instructions. This can be another sign that things just aren't quite right, that the code is probably in some sort of obfuscated state. That is, when you start to see functions that really don't make sense, this function doesn't really make sense, or instructions that you just don't see very often. A pop SS, for example, is one I don't see very often. Exchanges, yeah, not that frequent, but they're common enough. But a pop SS, that's odd. We can also switch to a linear view here, and you can see all of these bytes that are likely related to this function. But because IDA encountered a return, it stopped its analysis and it said, something happened here, so I can't go on. So these are all just good signs that this code is obfuscated. You're not analyzing the right thing. So that would mean that this, I'm going to rename this, and we'll say this is the unpacking stub. Okay, let's just real quick compare that to the unpacked version. So I'm going to open this up with IDA as well. I already had a database, so yeah, you know what? Let's just, that's all marked up and analyzed. So I'm going to change the name of the binary. That way, when I open this with IDA, I'll just get a new database. Let's see here. Okay, accept the defaults and close that output window. Okay, so now we're looking at the unpacked version. You can see there's the entry point. IDA calls that start. Here's our first call and our second call. Those were the only two calls that we looked at. This first call is a little different though. IDA is saying that this is null sub. And if we go into this function, it just does a return. So basically it does nothing. If you compare that to what we just looked at, right, here we have a bunch of logic. So the unpacked version simply doesn't contain any of that code. And now if we go to the second call, and here, I'll call this the unpacking stub as well, just to keep us kind of in sync. You can see that this also has much different looking function graph, different sequence of instructions. Looks like it's actually doing something important, which it is. So there's a big difference between the two. Now, if we go back to our YARA, what do we know about code 2 and code 3? Well, I'm just going to pick this match, code 2, and I'm going to copy those bytes, the pattern, and we can use, let's see, let's go to the password protected. We can do a search sequence of bytes, and we can actually just paste that in as long as we're searching for hexadecimal. I'm also going to check find all occurrences, and you do actually have to have this space between. It's kind of annoying. All right. There is the results. We do have a result right here. So let's navigate there. Now, this is where, let's go back to general, and I'm going to turn on opcode bytes. This value right here. When we look at a binary, we're looking at just the raw bytes, the raw binary data of that executable. Say we look at it in a hex editor, or when we create our YARA rules. When we look at that binary disassembled in IDA has interpreted those bytes for us and then provided the resulting assembly, or if we had the decompiler open, that pseudo C-like interpretation. When we add the opcodes, which I'll now do, you'll see that what happens is in our IDA view here, these blue values are now the raw bytes that IDA has interpreted as that instruction. So as an example, opcode 55, hex 55 is a push EBP. Opcode 56 is a push ESI, right? And it's actually these bytes then that become the basis for the pattern in the rule. So if we go back to this, where did we find that sequence of bytes for code 2? It's here. It doesn't highlight it real well, but if you just look at the first, here, let's open up the terminal. The first few bytes, 7D, 0C, 66AD. I'll go back to IDA, 7D, 0C, 66AD, right? This is then where the bytes came from. So this is what the author of that rule, whether they did it manually or decided to use some tool to identify this sequence of bytes and generate it, I don't know. I have my suspicions, but I don't know. But this is what those bytes represent. Now, do we know if this is a good pattern or not? Well, it's hard to say, at least at this point, if we're coming into this fresh, because you'd have to then take the time to understand what's actually happening in this function. And as you can see, right, unless you're doing RE work on a regular basis or you're comfortable with assembly syntax, it can take a little bit of time to build the context and understand if that is a good selection of bytes. And so maybe there was a tool that helped with the automation. It took that sample, it took a corpus of other samples, and it said this is the most unique sequence, therefore create a rule off of it. We can try to build a little bit of context further from what we've already done. And this goes to cross-references again. We can look at this function and you can say a cross-reference graph 2. So that'll be similar to the from, except 2. So all the function calls that lead to this function. And you'll see that it maybe not a surprise, but from the iText section, there's a call to the unpacking stub, and then this is 2 function calls later. So that is certainly code that is coming from that unpacking logic and appears to be quite unique to how Lockbit is doing things. So my confidence is higher, but without looking at all the code and really understanding exactly how it works, I can't say 100%. We also know that this YARA rule doesn't catch the unpacked versions. So, you can see that as a limitation. You might want to adjust or account for that. Maybe there's another rule that we create that is based upon, the packed or the unpacked or the unprotected version, or modifying this to help accommodate that. But it's good to know that there are potentially some limitations. I would actually be curious. Maybe I should do this: is to craft a rule for those unpacked versions, and then do like a retro hunt on virus total just to see how often those got utilized and found out in the wild and uploaded. They certainly would streamline the process of executing them on the system.
Josh?
Yes.
Since you got a moment to breathe.
Yes. Well, I was trying to not go too long, and now I actually went a little too fast. I think I feel like I'm talking real fast today.
So we have one question by George Gibbs. Is this byte sequence what is usually called shellcode?
Well, yeah, great question. So the byte sequence is these bytes right here. And I'm going to give you kind of a longer answer just because I have a little bit more time. If we just pick any of these executables and open it with a hex editor, for example, HXD, we can scroll down a little bit. Here's going to be our text section. And you can see that these are all the bytes that we were just looking at. These are protected, though, because we know from our analysis that these are protected. So we'd have to scroll a little bit further to find the unprotected. But this is just the raw binary data. Now, the fact that these bytes are wrapped in a PE file, when given to the operating system, it understands how to parse the PE file. All of this information up here at the top of a PE file, that's all header information. So it'll tell the operating system how to parse the remaining file, what sections there are, where they should be loaded in memory, what permissions they should have, where does the code exist, how to begin executing it. And that's what we're basing the rule on. Now, shellcode is very similar, except the sequence of bytes that we use for shellcode is completely devoid of a file format. So you see a sequence of bytes for shellcode, it's not in a PE file. And so the operating system doesn't necessarily know how to handle that. And getting that shellcode into memory to be executed then is the chore of whoever is trying to get it to execute. Malware authors will use it, exploit devs will use it, but it's just a sequence of bytes, and it meant to be executed directly by the CPU. But because it's not loaded by the operating system, there's a ton of things that it has to do in order to be functional. Imports is one, loading libraries and loading APIs. That also is something, oddly enough, that these binaries will do. It's a common obfuscation technique, is to dynamically it's generally referred to as runtime linking, but to dynamically import all of the libraries and APIs that the code needs after it's been deobfuscated. So it's something that it's not necessarily done the same way, but a lot of times shell code and malicious files will have to do that same task. So that's what we're looking at. So these would be opcodes and the bytes, and it's just important to understand what these represent if you're going to work with YARA rules at a low level. You may not like assembly or you have time to study it. One thing that can be a helpful shortcut, I am going to open up the decompiler. That's the function F5 key, or the F5 key here in IDA. And what you could also do is maybe a way to make it a little less painful. You can see that we're now looking at that same code, but it's pseudocode, so it's maybe a little bit easier to interpret. We could also use this if we were looking for potential code patterns manually, to say, oh, I want to look at the result, I want to look at the decompiled results. Maybe this is a good result here, or a good candidate based off of your analysis of the code. And then you could look at the disassembly view and pick out the opcode bytes, which would be these values here.
Okay,
So
we have
that would be another question, or another option that I meant to bring up.
we have more questions.
Yes, okay, great.
Okay, so from Michael Reed, would you agree that this approach should be taken when analyzing similar families such as lockbit 4.0?
Yeah, so there's definitely a process to using code patterns, and I think what makes it kind of challenging is just, if I were to create the rule like you saw, I would be curious. Not only other samples, having other samples that were claimed to be lockbit 3, to see what in these binaries changes. Do they intentionally change the unpacking logic, or is it consistent? It just uses that password in order to create the variation. And also looking back at other versions. Lockbit 3, for example, it's also called lockbit black. And I believe part of where it got that name was because there's code in here that was first identified in the Black Matter ransomware. And so it appears that it either used the code, or maybe there's some developer overlap. I'm not entirely sure, but I wouldn't have recognized that myself because I've never looked at Black Matter, but someone who has was able to identify similarity in the techniques, not 100%, because I believe Lockbit changed the technique a bit. But having that broader view into the other samples, not only other versions of Lockbit, but other ransomware, can be really helpful. And so, part of that is building a corpus. We talk about that in the course as well, is how do you build a relevant corpus of samples to help fine tune your rule to make sure that the patterns that you're picking are appropriate for the sample set. And I wouldn't say it's the easiest thing to do. It's kind of a chicken and an egg problem, in that if you have a sample that hasn't been detected yet, grooming a nice set of representative samples then it can be challenging.
There's more.
Okay.
So Kate Lucero is asking if you can show the YARA rule again. Then you have Nitish Chowdhury, I'm sorry if I'm butchering several names, is asking what these bytes are doing. Is there any malicious pattern here we are observing? And how can we identify these malicious patterns?
Yeah,
well, there's one last one.
Okay. Here's the rule. I'll just share the link in the chat. There you go. So if you'd like to take a look at it. So there's the rule. Again, community crowdsourced, somebody, it looks like from BlackBerry, is the author, and they uploaded it and shared it to the world. And so it's ours to do what we want with, to see if it matches our samples, which it did to a certain degree, probably the most important or most relevant. The second question was about detect the code itself.
Yeah, it's in the chat in case you want to check it.
Yeah, so detecting the malicious patterns and detecting the code patterns, again, that becomes, I think, a part art and a part science. There are projects, if you're familiar with Florian Roth, he does a tremendous amount with the YARA community. He has projects out there that help to take binary sample sets and a representative sample and try to pick out unique sequences of bytes to create these rules. What you end up doing then is you spend a lot of time with not only getting the samples that you want to base your rule on, samples you of course don't want to base your rule on, and doing some binary diffing, disassembling, looking at those sequences of bytes, trying to figure out if they mean anything, or automating that process, and then using the sequence that it spits out to say these sequence of bytes show up in the samples that you want the rule, and they don't show up in any of the samples that you don't. And so there are some tools to help with that, and those are great to check out. I think you're probably going to get higher fidelity if you have the time to do this sort of work, but of course, the time commitment now goes up pretty extensively. And here, a lot of it then will boil down to doing the actual code analysis. And so, in our sample here, I'm just navigating back to start. I'm taking the long way, I guess. I could just go to start, sorry. We're able to do a little bit of triage, and we know pretty concretely that this is the unpacking stub. Now, without looking at the code, I don't know how the unpacking stub actually works and how unique the approach they're taking is to lockbit versus other samples. The fact that I didn't see any API calls, it's all appears to be custom code. IDA didn't recognize any libraries, say base64, maybe RC4 or some well-known encryption. I can't say that it's not there, but there's no sign or evidence of it right now. So I think it's a pretty good place to start. Now, what sequence of bytes? That's also kind of challenging, because when you look at the code, I might have come up with an entirely different sequence of bytes than what that rule came up with. And that might just be, hunch or intuition, or looking at the code and understanding and saying, oh, this is actually like this block right here followed by this block right here is a really unique way of resolving. That's hard to do, because what I have found over the years is I'm surprised. I'm usually surprised at, and you kind of saw it with Pancho's demo earlier, the things that show up in malware also show up in a lot of benign software, different code patterns or sequences of bytes. And so it can be challenging. There isn't anything then outright malicious in this code, because this is just unpacking, but it could be, and likely is, unique enough to be the foundation of a really solid YARA rule. Hopefully that answered the question. I tried to not become expert level in my time in academia of talking a lot but not answering as a form of deflection. Okay. Do we have any other questions? Because I think that's really all I wanted to talk about. Again, there's a lot here, and if you're not familiar with the reversing process in IDA, there is certainly a bit of a learning curve. But I hopefully, if you take anything out of it, it's if you haven't seen the process before of how YARA rules such as this, what they actually mean and represent, then hopefully this could help. You could consider in a rule like this, if I were the author, you could take the code from the binary and just add a little bit of context, even if you just said, hey, this pattern begins at, whoops, sometimes my mouse gets really jumpy. This wasn't the original location, but you could say it starts at this address in this binary. At least that gives someone a more immediate place to go and take a look. You could copy all of the code out, right? We could switch to this listing view, and this could be a comment that adds, of course, a little bit more cruft to the rule, but it's a good reference. So then anybody that's looking at it doesn't have to go back and dig through, like we just did, dig through IDA. It wasn't an extensively long process, but it does add a little bit of overhead in order to understand, what these patterns actually represent. But those are suggestions. I don't think there's any right or wrong way. There's just the way that makes the most sense for you and how you're maintaining your rule set. And that could be an important part when it comes time to look at retiring or updating a rule. What was it based on in the first place? Strings are oftentimes a little bit more clear because their string. It's ping, or it's decrypted, or your files are protected, or something like that. Pancho, did you have anything you wanted to add?
No, I think we can answer one more question, and then maybe if you have something on the slides to show that you didn't show, it's a good moment to please.
Okay.
Let me read the last question. Have you used rule generator tools like YARA? If so, what have you found are the advantages and disadvantages of using those types of tools? Let me answer at least the first part. We are going to talk about tools that help you create YARA rules in the workshop, and the advantages and disadvantages. But basically, automatic generators, they usually grab uncommon patterns inside the files, and you don't understand what they are catching. So we are trying to teach you how to create YARA rules that you can understand and that you can share with other people, so that they also can understand them and not just grab unique patterns. So this is kind of a disadvantage for the automatic generators, but of course the advantage is like the speed in which you can find unique things inside files. So if you have a good corpus of files and you want to create files and test the YARA rules against them, it will be really quick to have something unique for it. If you add something else, Josh, please.
No, I didn't have any slides. I think Peter might have some outro slides though, but if we're available, easy to find on social media. If you have any questions about the workshop or the upcoming workshop at SuriCon, hope to see you there. And thanks OISF-Suricata, Peter, Juliana for having us on the webinar today, and everybody for joining.
Thanks, both of you. I will interrupt before Peter starts. Someone is asking, how can we implement YARA rules with Suricata? What I can say is that if you have the opportunity to join us in Madrid in November, you will definitely have a lot of time to see that happening, and they will explain way more, because it will be 2 days training with a lot of content related to that. This was just like to make everyone want to join us.
Yeah. And that, that, yes, I think you're right on the question. YARA is primarily, you're going to find it in EDRs and things on the endpoint. I wouldn't say it has a direct role in Suricata, because Suricata has its own rule detection engine based off of the network traffic. Now, Suri does have file extraction. And so you could, in theory, use it to extract files from the wire, drop it into a system that then processes those files. That could include things like YARA or a sandbox or something. So I think there are some ways to sort of connect the dots. And that was the whole motivation behind the course that we're going to be offering. Suricata, so basic rule writing, the YARA, and then the Sigma, so that you have network, you have endpoint and file, and then you have logs and behavioral, so that you have the 3 primary domains, as it were, to create detections and hopefully improve security. And then talking about all the malware analysis kind of stuff that goes on to help generate those rules.
Thank you, Josh and Francisco. I'm going to go ahead and share the rest of the slides, but I do have 3 questions though from me, because I was actually following you folks, and I wrote some notes in here and I have a couple of questions here. Okay. So let me go ahead and I'm just going to share the do you folks see my slides
Yep, looks good
correctly? Okay. All right, just want to make see them all. This slide that I have here, it's about celebrating our 10th SuriCon in Madrid. We have 3 days of talks. We have a couple of days of 3 different trainings. Josh and Francisco one will be one of those trainings. It's a possibility to meet the community, meet the developers, meet some of our consortium members, discuss about a lot of ideas, features, face-to-face, which is always a great benefit. So if you haven't, please look those dates. The training sessions are November 11 and 12, and SuriCon itself is November 13, 15. It's going to be a lot of fun. Usually is any SuriCon that I've been so far, including the virtual ones, although this is face-to-face, and it will be a great possibility to meet a lot of professionals. Please join the Suricata community in any way, shape, or form you can. It's a possibility not only to connect with developers, but to connect with community, to connect with expertise, to connect with knowledge, to share ideas, or to get actually input is very important for us, for the people that are actually actively working with Suricata to get more feedback as well. Don't be afraid to reach out. We have a forum, we have a Discord public channels where you can actually, let's say, walk in, highlight Josh and Francisco, for example, and be like, hey, I saw your webinar, and ask more questions about it and things like that. Please don't hesitate. We also have, as a part of these pre-SuriCon web series webinars, a follow-up with using Suricata log to analyze your events with Jose Nunes on September 19, 4 p.m. UTC. Don't hesitate to go in and register, because they're all interesting ones. And thanks, Jules, for pushing up and keeping up the good work. They're much appreciated. Last but not least, we have a Suricata roadmap discussion, October 17th. You're more welcome to join. There's 2 sessions and a lot of discussions, and actually live feedback and live interaction is taken time during those sessions. So please don't hesitate. Pending that, if I've done a good job rushing through those slides, for which I apologize if that was the impression, it was not the intention. I'd like to ask a few questions that I have on my book here, and please excuse me, some of them might be novice because I'm not that well versed into reverse malware engineering. Question for you, Josh. How do you folks differentiate, or how can you differentiate between, let's say, log bit versions? You have, version 4. How do you know it's 4, not 3? How do you do that in general? What's behind it?
I've not had to do very much of that to very little of that in my career, so I can't. I like to speak from experience on a lot of the technical stuff, and I just can't. I would imagine that there's a number of ways, though. Some of it might be because we have folks tracking where they're selling this stuff in underground forums, and they promote, just like a lot of software does, new versions and new capabilities. It might be in the case of ransomware, it might actually just be in the ransom message. Sometimes there's internal information that you can find that would indicate the version number. Sometimes if it's not clear, maybe it's more of a nation state. You're just, you have someone with the experience that monitors the evolution of that particular strain or capability, and they can just say, hey, this is very similar to this previous sample. I think it's a new version, though. And so they make the call as the team or the folks looking at it regularly and decide to give it a new version. So I think there's a number of ways that it could happen. Usually the easiest, though, is when they tell us lockbit 3 is here.
Got it. Okay. So it might be mixed, both analysis and actually, let's say, intel.
Yeah. Or probably for a lot of teams out there, they're not going to have that level of insight into reversing things, and so they wait for companies like Mandiant, who has threat intel teams, to say, hey, we've seen a new version of, and we're calling it, and then we just follow along with what they're establishing for us, because they have the history and the expertise to help identify those version changes.
Okay, super. Another question, second to last, and then my last question. But it's very interesting, folks. Thank you very much again. So you mentioned in DAI, you usually, one of the first things you do is look at the signatures.
Mm-hmm.
a signature, and then you mentioned you also you're creating YARA rules. Are those similar in capability?
Yeah, if you look at DIE in particular, it has its own signature engine, and you can pull up its rule set if you just dig around in the tool a little bit. It's pretty easy to find. It's kind of a JavaScript-esque syntax. I haven't really spent the time to figure out exactly what's going on there. It's not quite YARA though, but it looks very similar. I would imagine you could probably convert a lot of those rules to YARA or a series of YARA rules if you were so inclined. Detected Easy also has the ability to just take YARA and scan as well. So you can also add your YARA rules to Detected Easy and scan away. So, but you know, its rule engine, if I remember correctly, is very YARA-like. You know, it's a sequence of bytes, it's strings, it's characteristics of a file, entropy, and other stuff that you can all do with YARA.
Thank you. And my last question, and I have to really content myself. Apologies. How easy or difficult, respectively, is it to do attribution when you're doing reverse engineering? I mean, some parts of code or code patterns apparently could be similar, but that doesn't mean that the code was developed, let's say, by the same person or copy-pasted from somebody else or the same organization. So just out of curiosity, is it easy? Is it difficult? How do you guys do it?
Well, from like a reversing perspective, I'd say similar response to the first question with versioning. It can be pretty challenging, just because it's common for reverse engineers to look at a sample, reverse the sample, provide indicators or behavioral aspects of it, and then move on. You know, sometimes it does take, and oftentimes it does take, special teams that are focused on, you know, certain groups or certain actors to build that familiarity with their tools, their tool set, and the history of their code. I don't do attribution. I wouldn't even bother or try. I don't do it professionally. I don't do it on all my side stuff that I do, because it's just really challenging. And then you add in, I know, like false flags and stuff. We talk a little bit about, we have an exercise in the workshop with some, it was really popular. It was from the Olympics.
The Olympic destroyer one.
Yeah. I don't know, Pancho, if you want to talk about that, but you know, even little things like that can really make it challenging, because you just have to understand oftentimes the code and have a way to look back and like compare. And it is demanding. So I don't typically do it.
That's, for example, in all the samples that I showed of ransomware, they all announced who they were. Like in the ransom message, everyone had their names in the title. But for more complex malware, it's much more difficult. But for these kind of things, when you have like a ransom node and they want to present themselves, that's pretty easy.
Got it. Thank you very much, folks. Apologies if my questions were a bit of no wise and all that stuff, but I was just genuinely curious. Much appreciated.
Great questions.
Thank you, sir. Jules, do we have any more questions? I don't see any at the moment, at least.
There's one.
There are? Okay.
Yeah, from earlier. I believe Josh mentioned this, but just to make it more clear, how can you identify when it's obfuscated or if it contains a pattern?
Yeah, so the obfuscation is, I mean, that's kind of a multi-step process. You know, I mentioned it earlier, just that I very rarely will I go right into IDA with any sample. I always start with basic analysis, using tools like DIE. You know, I didn't dump strings just for the sake of time, but, you know, looking at strings, the presence of strings, the absence of strings, that can tell you something. Our packed binaries, and even the unpacked samples with Lockbit, neither one of them presented any reasonable strings. And so that would tell you that, you know, those strings are protected, because obviously there's a ransom note. Like if you ran it in a sandbox and you let it ransom a system, you'd see ransom notes and other things. So obviously those are protected. The lack of imports, imported libraries, imported functions, looking at, you know, entropy across the file, looking at section names, putting it in a sandbox, letting it run, and looking at some of the process behavior. And, there's a number of different basic, what I would put in that sort of basic triage that I would be looking for. Now, that triage is maybe different than maybe an analyst, SOC analyst is just who's just trying to get to, is this bad or not? And if it's bad, what is it? I look at it in the context of it. If I'm going to open this up in IDA or do any sort of reverse engineering, what should I anticipate? And I still look, because sometimes you'll get a signature, for example, Detected Easy. UPX is an open source packer. It is still commonly used by both benign and malicious software. So if I get a sample and I open it in Detected Easy right away and it says, oh, this was packed with UPX, well, the first thing I'm going to do is unpack it with UPX, because there's no point in analyzing it any further until we get to that next stage, and then take that next binary, start the process over, and see what we have. And so there's a number of techniques to do that. So if you're looking for resources, I would say basic static and dynamic analysis, basic triage. Those will be the areas that you'd want to focus on.
Much appreciated. I don't think we have any other questions.
No, I think
Okay,
we're good
that's
now.
super.
Okay.
Josh, Francisco, thank you very much again for the time and effort all you guys are spending on that. Thank you very much for actually doing a training at SuriCon. Looking forward to see you live there. The rest of you folks that are with us on the webinar, this is a recorded webinar. We will have it posted pretty soon, and looking forward to see all you folks as well at SuriCon in Madrid. We'll be very, very appreciative for that. With that, I'm going to go ahead and actually stop the recording.
All right. Thanks, everyone.
Thanks, everyone.
Thanks, folks. That was a